All right, 4.1, electron arrangement. So the quantum mechanical model, how does it differ from Bohr's? Remember, Bohr said that electrons can zip around on specific orbits around the nucleus. We know exactly where they are. They could jump from one energy level up to another orbit and then crash back down and give off light as they do that. He was onto something there. The only difference with the quantum mechanical model is that we don't know exactly where they are. We do know that they're zipping around in certain regions within the electron cloud, and they're probably in those regions most of the time, but they're not always there. Just like you, if you had a ticket to a game or a show, you're probably in your seat that the ticket describes, but you might not always be there. So same thing with the electrons. Now that electron cloud is divided into energy levels, 1, 2, 3, 4, 5, I can keep going, and then those are divided into sublevels. Energy level 1 just has S, you get the idea here, and then those sublevels have certain orbitals. Orbitals you could think of like seats for two. So if we're looking at the S sublevel, it's round. There's only one of them, and you can put 2 electrons in. The P, it's more of a figure 8. There's 3 of these orbitals. I should be drawing these on different axes. But you put 2 in each, you get 6 electrons. D kind of looks like a clover, except for the weird one in the middle there. And 2 in each, and there's 10, because there's 5 of them. And F is really complicated, but 7, and then you can put 2 in each. So you should be very familiar with the breakdown. And if I said, for instance, what's found in energy level 4, you say, well, there's 4 different sublevels. There's S, P, D, and F. And then you say, in the S it can hold 2, in the P it can hold 6, in the D it can hold 10, in the F it can hold 14. And if you add them all up, you can figure out how many electrons it can hold, etc., etc. So you should be able to answer questions about the breakdown of the energy levels, sublevels, and so forth. You should also be able to look at the periodic table, an extended one and a typical one, and figure out the different sections or the different parts. This is the S block. These guys always end in S1. These guys always end in S2. This is the D block. These guys end in D1 all the way over here to D10. This over here is the P block. These guys end in P1 through, actually let me dip here, P6. Helium ends in S2. That's why I omitted that there. But this is the P block. And finally here is the F block. This is F1 through F14. Now this is the regular periodic table. The extended periodic table, I don't have a picture of here, but you should have it in your notes. This whole section here, 57 up through 70, fits right in there. So picture taking this whole section and moving it way over there and scooching this section up in here. So you end up with more of a S block, F block, D block, P block, and there's your little helium. So this is what the official periodic table should look like, but because this is way too long and wide, we pulled this section out, put it down below here, and close the gap between the S and the D. And if you use your periodic table, whether it's the extended one or this one, it basically writes the electron configurations for you. Just keep going across. 1s, 1s2, 2s, 2p, 3s, 3p, 4s, nothing, 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 and then we hit 3d. Remember, d's are one behind. And then we hit 4p, and then 5s, 4d, 5p, and then we hit 6s. 6s, and then we finally hit the f's. F's are 2 behind, so it's 4f, then back to 5d, and then back to 6p. So if you use your periodic table, you know when you hit the f's. You don't hit them until you get to the 6th row, right there. And you don't hit the d's until you're in the, let me erase this. You don't hit the d's until you're in the 4th row, because this is when the d's start. So 4s and then 3d. Over here, 6s2, and then this is where the f's come in. So 4f14, and then back to the 5d, and then back to 6p. So again, you should be able to use your periodic table to write the configurations. Oops. Some things to keep in mind when doing the configurations. The off-bow principle, Remember, it starts with the letter A. You're going to fill everything in order. If I said, tell me the ABCs, you're probably going to start with A and tell me the ABCs in order. You're not going to jump around and tell me A, L, Z, K. You're probably going to do A, B, C. Same thing with the electrons. Fill them in order. Least amount of energy to the higher amount of energy. That's why the 3D here gets filled after the 4s, because 4s has less energy, then 3D has more energy. Pauli exclusion, you should be thinking exclusion. Anything other than 2 electrons get excluded. Think of sneakers in a shoebox, you can only fit 2, and they have to be oppositely turned, opposite spins. And finally, Hund's rules, like strangers on a bus. You probably wouldn't go sit next to a stranger when there's lots of empty seats. Same thing, these 2 negative electrons are not going to sit next to each other when there's space to spread out. So if you're given the opportunity, like down here in the P section, you're not going to force, here's your 3 P's, you're not going to force this electron, this one, and that one to all sit together when there's an open spot here. So put 1 in each, and then you can start doubling down. Oops. All right. Okay, so electron configurations. Just take a look at these. Make sure that you know when the D section pops in. And finally, as we're going through this, let's talk about valence electrons. Valence electrons are the electrons in the outermost energy level. So for chlorine, there's 7. So if I was doing the electron dot structure for chlorine, it would kind of look like this, because there's S2P5. Over here, yeah, there's electrons in the first energy level, but that doesn't matter because there's electrons in the second. They don't matter because there's electrons in the third energy level. A lot of them, but they don't matter because there's electrons in the fourth. There's only 2 of them, 4s2. The 4p is 0 right now. There's nothing in there. So we only have to worry about 2. So iron, Fe, would have 2 valence electrons. Sulfur's got 16 electrons. Notice, if you have to draw this, you are going to label each one of these. You're going to draw 3 lines. Even if you don't fill them all, you still draw 3 lines for the P's. If you were doing D's, you would draw 5 lines. Even if you only put 1 electron in it, you would still draw 5 lines. Up, down arrows, I think that's about it. And again, for valence electrons, if you looked at sulfur, you would count the S's and the P's of the highest energy level. So 2 plus 4 is 6. Sulfur would have 6 valence electrons. What do the following elements end in? Again, just check your answers. Let's see how you did here. And noble gas shortcut. Aluminum, you look at the noble gas that comes before it. So aluminum, what comes before aluminum? Well, neon. Aluminum's here, so you go back, you get to neon. Neon, and then you start at the row aluminum's in. So 3s2 and then 3p1. And there's your electron configuration with the shortcut for aluminum. Now aluminum is 3s2, 3p1, Al. It's got 3 valence electrons. Aluminum would like to lose 3, so it's going to eventually become a +3 charge. And there's those 3 electrons that it wants to give away. And aluminum, little side note here, aluminum is a metal. Yes, it's on the zigzag line, but aluminum is just a metal. It's an exception. It's not a metalloid. All right, the next one you had to do was palladium, number 46. So here's palladium. You're going to go back to get to krypton. So you write krypton, that takes care of 36 electrons, and then you pick up with the 5s, and then you go back to 4d. So 5s2, 4d8. In terms of valence electrons, we don't care about the 4th energy level because there's some in the 5th. So palladium, it's got 2 valence electrons, and that's all we care about. Just make sure I have the right symbol. All right. Over here, you have to figure out valence electrons. Again, check your answers. There's your aluminum, 3. Over here, you're looking for the highest coefficient, which is not the 3, so we don't care about that. We just care about the 2 there. All group 1 elements always have 1 valence electron. Neon is in group 8, so it's got 8. Aluminum's in group 3, so it's got 3. Magnesium is in group 2, so it's got 2. So you should remember that your valence electrons matches your group number for almost all, with the exception of, with the exception of the D block. There's 1 valence, 2 valence, 3, 4, 5, 6, 7, and 8. This guy has 2. That's an exception. These guys, who knows what they're doing? You have to look them up to figure out what charge they're going to do. But they all have, for our intensive purposes, 2 valence electrons, because it's always going to be the 4s2 or the 5s2 or the whatever. These Ds don't count because Ds are always 1 behind. So we're going to write down the fact that they have 2. So if I picked chromium, chromium would have 2, but chromium does weird things. It doesn't always follow the rules, so chromium could make a 2 or a 3 charge. And finally, these guys do have, tin and lead. They do have 2 and 4 valence electrons sometimes, and you can see by the charge. You officially would write down that there's 4 valence electrons because they have the S2 and the P4, or P2 rather. S2, P2. That equals your 4 valence electrons. But sometimes it just gives away those 2 valence electrons and it ends up making a +2 charge. So they do some weird things, but in terms of valence electrons, since it's in the P block, it's a representative element, just go with 4. Okay. And helium, don't forget, only has 2. And that is the end of this section. Now, next we'll talk about electrons jumping around.